Okay. Should I just start? Okay, fine. So, good morning, everyone. Thanks for coming. So this is the first time I'm on air, as I can see over there. Thank you very much to the organizers for inviting me here. Especially thanks to Rama. It's a great place to be. It's my third time here at the Newton Institute, and always find it amazing what an intellectual place this is and how much it encourages discussions between people, because given this architecture of the building, there's absolutely no way you can hide. It's just impossible. Okay, so what I would like to share with you today is some work we've been done over the last 3-4 years on stochastic optimal control problems that arise in models of optimal portfolio liquidation. So what I'm going today is something I normally hate. I'm taking the attitude of a mathematician, saying that there is an economic motivation somewhere for a particular mathematical problem, and now let's just look at a mathematical problem and forget where it comes from. And then maybe later on, of course, there is a message that one might to take away from these models, but so we are not going to take the models to the data. We are not going to discuss too much the pros and cons of the modeling. We really take these portfolio liquidation models, illiquidity risk, as a motivation to look at a particular class of mathematical problems. So this will be essentially 4 separate lectures corresponding to more or less 4 separate papers, all of which you can find on my webpage. And the first paper I would like to present is based on joint work with my PhD student, Pauline Greve, and Eric Serret from Paris Dauphine. Eric is an expert on PDEs. And there's a story I'd like to tell about how I got in contact with Eric. So Pauline and I were working on the stochastic control problem, and sooner or later you end up with a PDE. And the question is, can you prove that this PDE has a solution? And it was a very particular one. And very often what I do, if I have a mathematical problem but not the answer, I show it to Ivar Ekeland. Because chances are he either knows the solution or he knows somebody that knows the solution. So I showed the problem to him, and he thought about it for a while. So, well, I don't really know how to address it, but talk to Eric. Good. So I walked over to Eric, knocked on his door, showed him the problem. He said, yeah. And immediately he started doing computations. And I think these PDE people, they have an enormous supply of methods. And then he just tried some of the methods that he knew to this equation. And he had a notepad, and he was writing some ideas, was shaking his head. Okay, that method didn't work. He tried the second one. The story repeated itself. And he started the third one, and he looked up at me and said, you don't have to wait for me. I'll get back to you if I have something. So I thought, well, maybe this is not going very well. He has no interest in this. So I walked home a little bit disappointed. The next morning, I checked my emails. And in my inbox was an email from Eric, sent the very morning at 2:40 a.m. A handwritten note with an outline of a solution to a particular example. So this is how Eric came in. So the much of the credit really for this paper and for the approach in particular needs to go to him. Okay, so is this working? Help. Yeah. Nope. Maybe I unplug it, plug it back in. Nope. Okay, anyway, so I use this. This isn't working either. Okay, but I think my computer crashed. Well, okay. Fine, let's do it like this. So here's an outline of the 4 talks I'm going to give. So we start with these portfolio liquidation model under market impact with actually price-sensitive market impact. In this first lecture, brought about the first maybe 45, 50 minutes. Then there will be 2 lectures on an extension of these, where the underlying stochastic dynamics is no longer Markovian. So if you have a Markovian stochastic control problem, you end up with an HGB equation, which is the PDE. If you have a non-Markovian optimal control problem, you end up with something which is more complicated. And depending on how you set up the problem, you either end up with a backward stochastic differential equation or with a backward stochastic partial differential equations. So I'm going to discuss these approaches as well. And then the final presentation, it's actually the oldest paper, but it will be a slightly different model. It will be a model where a trade that you submit has both a permanent market impact as well as a temporary market impact. So temporary market impact basically means you submit an order and you incur a cost of doing so, but that cost is only occurred by you. So it's like a one-time thing, a little bit like a transaction cost. For the permanent market impact, the idea is that an order that you submitted 5 minutes ago, the impact of that you already also feel now at this very moment, and maybe the next 5 minutes as well. So in these settings here, the emphasis, the focus is on the value function as well as the nature of the trading strategy. Here it's a little bit different because we have different kind of market impacts the way we model this. We cannot really make an HAB approach here. So we use stochastic maximum principles to get an understanding of what the optimal trading strategy should look like, what the nature is. It's a little less transparent, but there's a very clear message how this optimal trading strategy should actually look like. Okay, so let's start a little bit with motivation on portfolio liquidation models. I would say that up to maybe a few years ago, when you started reading a paper in mathematical finance, one of the very first sentences was, let the price process be described by a semi-martingale X. And then the idea was that, okay, you have an exogenous price process. In whatever amount you trade, you can trade it at this exogenally given price process. So I think, at least with the financial crisis, we have learned that liquidity risk, which was prior to the financial crisis a secondary risk, really has become a primary source of risk today. So while this idea of trading at exogenous prices might be correct for somebody like me, it is certainly not correct for an institutional investor that moves around large blocks of shares over a relatively short period of time. So as a rule of thumb, if you trade more than anywhere between 1 to 3% of ADV, ADV is average daily trading volume, you move prices. Now the first time, 10 years ago or so, I came across large investor models, I thought that, well, if you trade a lot, it should be good. You buy a lot, you get a discount. This is what people in inventory management do. Now, of course, in finance, it's the exact opposite. So you trade a lot. It means that if you trade in a limit order market, it means that you eat very deep into the book. So there's only a limited liquidity available for trading at particular price levels. So trading a lot is actually bad for you. You have this market impact, therefore you have trading costs. And the question is, how do you optimally transact in such a market? I would say from an economic perspective, this is a very old hat. Economists, Easley O'Hara, for instance, they have thought about optimal block trading for ages. I mean, some of the seminal papers, they date back to the 1980s, 1990s. But they had, when they looked at this problem, I think they had a different motivation in mind. For them, block trading was very often associated with informational asymmetries. So the question is, like, why does somebody want to trade with me? Why is this person all of a sudden unloading a large number of shares either on me or on the market? What is it that this person knows that I don't know? And the kind of suggested remedy against this was stealth trading, namely not trading a big chunk of shares at a particular time, but rather split large blocks of shares into smaller ones and trade them over a certain period of time. I would say mathematicians have identified this topic only much later, and with a different focus and from a different perspective. I would say much of the work that we have seen in the math finance literature looks more at structural models. So you start with a model that tells you how much it costs to trade. You don't really care why you trade. And the reason is that most of these models, I think, are motivated by liquidity trading. So there's just a trader, and the trader needs to trade. So if you think of an investment bank that trades on behalf of somebody, so the trader has the order to unwind a certain position by the end of the day, and he doesn't really have to care why, but what he has to care about is how much is it going to cost him and what he should benchmark his cost of trading against, because this is what, at the end of the day, he has to charge his customers. Okay, so the focus, I think, in math finance is more on liquidity, not so much on informational asymmetries. So, if we look at these models of portfolio liquidation and look at them from a stochastic control perspective, they give rise to a particular new feature, and the feature is that you have a control process, which is the portfolio position that you have. You start out with a certain number, let's say 1 million shares of Deutsche Bank, and in the end of the day, you want to bring this down to 0. And by 0, we mean 0. We don't mean 5. We mean 0. So you have a situation where you have a process which you control, and you put an extremely strong condition on the terminal state of the process. Now, this translates, at the end of the day, in some form of singularity for the value function. And the question then is, how do you deal with this value function? How do you deal mathematically with the PDE that describes the value function, which has a terminal state constraint, singular state constraint, or with the BSDE, or with the BSPDE, or whatever object describes your value function. And this is exactly what I would like to do today. So by the way, feel free to interrupt me at any time. I think we have more than enough time, so they gave me 3 hours.
What is BSDE?
Sorry?
What is BSDE?
So BSDE is backward stochastic differential equation, and if you have the P, it's a partial differential. Okay, but the first presentation now will be all about just PDEs, because we are in a Markovian framework. Okay, now, why do we care about illiquidity from a market microstructure point of view? Well, because most of the trades nowadays are settled through limit order books. What is a limit order book? A limit order book is essentially just a record of available liquidity at different prices. So the simplest assumption is that you can trade a fixed number of shares at any particular price. So if you have like 100 stocks standing at each price level, you want to trade 300 stocks, then the price for the first 100 is, let's say, 100, then for the next 100 it's 101, and then at 102, so on average you pay 101 if you buy, whereas the book value would just look at what is the best available price at this very moment. In these markets, you can essentially submit 2 orders. One is active orders or market orders, so you send them for immediate execution, which means that you transact at whatever the best possible price is at this very moment. The other possible order are passive orders. Passive orders cannot be executed at this moment. They are submitted for future execution for at least 2 different reasons. Either because it comes with a price limit. You are not ready to trade at the best available price at this moment. You want to purchase the stock cheaper. So you submit a limit order saying, I'm ready to pay only 99 for the IBM stock, but right now it trades at 100. So your order is stored in the book. Or, and this is what we will actually focus on, because you go to a different market venue, such as a dark pool. What is a dark pool? A dark pool is a trading venue, which I think has been around for at least 25, 30 years. But it's been in the center of attention only recently. A dark pool is a trading venue where you can submit orders, but you don't know whether matching liquidity is available in this dark pool. So as the name suggests, it's dark. So Rama operates the dark pool, so I can send a buy order to Rama's dark pool, and if at that moment Rama has matching liquidity, then he executes my trade, and he executes my trade at a price that comes from another venue. So Rama looks at the prevailing price at the London Stock Exchange. If he can match, he matched my order at a price prevailing right now at London Stock Exchange. If you cannot match, the order stays there for a little while and waits for the arrival of matching liquidity. So this is a form of passive order. And what is the benefit of this dark pool? The benefit is that if I'm executed at a price that comes from elsewhere. So I have much less market impact. The downside is I don't know if or when I will be executed. So there's a balance between trading in a primary venue with market orders at a particular cost, or ideally trading in the dark pool at no cost but having the additional uncertainty of execution. The reason we use this dark pool for passive order modeling is that we don't really have to worry about what the impact of the passive order is. Like what, okay, I should maybe at some point turn my wireless off. Yeah. Okay, let's leave it like that for a second, and I'll get back to the precise motivation of this dark pool trading later. But again, so the idea is you have these different types of orders. One submitted for immediate execution, where it comes with a cost. The other one submitted for possible future execution, which ideally incurs no cost, but there is the uncertainty of execution. So if you submit a large order to the dark pool, you're not going to get executed anytime soon. You have a bigger chunk of shares that you now have to execute in the primary market, which then of course occurs even higher cost. Okay, so here's the benchmark model, essentially the Ulrich-Horst framework where you only have active orders. And I think that the reason why this Ulrich-Horst model had such an impact is that they found a mathematical approach to block trading, which actually works, which is tractable, which gives you a solution. So here's the idea. The idea is that you start out with a certain number of shares, which you want to unwind by some time capital T. In practice, maybe that's 1 day. Okay, so you can trade in your market at a particular rate. The rate is Xi, so you have an absolutely continuous trading strategy. So you unwind your position at this rate. So at time t, this xt here, what you have minus what you have already sold, this is your portfolio process. And there might be a benchmark. There might be some stochastic factor, which could either be the price at which you trade. It could stand for the available liquidity. So it could stand for trading cost as well. So in this setting here, we really want to think of this as a price. Later on, we just consider or view this as a stochastic factor. And then the optimal liquidation problem is typically of this form. There's a cost functional additive in time, which depends on your trading activity at that point in time, on the prevailing price, as well as on how much you have. You look at the expected value, you want to minimize that, but subject to the liquidation constraint at a terminal time. So and it is this liquidation constraint at a terminal time that gives you a singularity for the value function. So
why is it T minus? Why can't you have a lump trade?
But I think that depends on how you set up the model.
Because in these papers by Gadron, everybody else, they do a scheduling of trades, and if at the end you are not able to execute, then you sell everything at the last minute.
So the last model I'm going to show you allows for this discrete trades. The first one I show you don't, because it's just math. I mean, you need different mathematical tools to address these problems. If you restrict yourself to absolutely continuous trading strategies, then you can basically do HJB. If you do singular trading strategies, you allow jumps in between.
Only at the end.
You need and at the beginning.
But given that ST is exogenous, no?
Yes.
So then, how can you satisfy the constraint with you want?
I show you. First of all, in a simple benchmark model, S drops out. So the assumption is always that S is some sort of martingale, and because of that assumption and taking expected values, it at the end of the day, in the simple setting, drops out of your control problem. first answer. Second answer is that as long as this S is continuous, you can, in a way, you can still enforce this. Let me put it this way. And
I mean, the subtlety is that S is not the actual price; it's some fictitious price.
Let me move on to the next slide. Then you'll see how this comes in. I mean, the question is, what is F, right? But I mean, anyway, the abstract setting is of this form: a cost functional and this singular terminal state constraints, which for the value function means that if you don't liquidate, then your cost is infinite at the terminal time. If you liquidate, then the cost at the terminal time should be 0. So question is, how can we deal with this problem?
And S is not the price of the share. What is S?
S? Well, think of S as being the mid-quote. So the difference between best bid and best ask. I mean, what they do in practice, they have some benchmark against which they measure their cost of trading. The simplest benchmark would be the mid-quote. But another benchmark, but this benchmark really then gives rise to non-Markovian control problem, is called VWAP, volume weighted average price. So VWAP is you take transaction prices, you multiply by the volume transacted at this price, and you average this over time. So there you would have a performance functional that really looks at like an average of something over time. And this VWAP is, in a way, tells you how costly your trade, if you carry it out now, is relative to the past. Okay. But I'm going to show you a list of possible S's along with a list of possible F's on one of the next slides. Okay, simplest case, take S to be some margin, a Brownian motion. And then think of this Brownian motion as being your mid-quote price. And the actual transaction price for you is not what you would get in the market, but you move the price in an unfavorable direction, namely according to how much you trade at the time and according to some market impact factor eta. And this market impact factor, think of this as being a constant right now, but later we want to make this random. This market impact factor could, for instance, tell you how much liquidity is available for trading at the first best price in your order book at this moment. Okay, so very often these papers assume you have a block-shaped order book. So the amount of liquidity standing at every price level is a fixed number, in which case this eta factor would just be the inverse height of the order book. Okay, so eta tells you how costly the trade is, and then the actual transaction price is this benchmark price, which later on drops out of the equation anyway, minus your cost of trading. So if you then look at the liquidity cost, what is liquidity cost? Liquidity cost is book value. Book value is what I have times what it is, well, in theory, worth at this point in time, at time 0. So what I have times the prevailing price. And then I subtract from this the revenue that I actually collect from this. And the revenue looks at this actual transaction price, this S tilde process, and the revenue is this fellow here. So this splits into two terms. One is this stochastic integral here. And now you see why we make the martingale assumption for S, because now we take the expected value and this guy drops out. So this is why it's not so important what S really is. And the only term after taking expectation that we are left with is this term here. And now so our F now would just be eta times psi squared. So what happens here is that we start out with a stochastic control problem, and at the end of the day we end up with a variational problem, because this is now a completely deterministic problem.
But here, so you directly write things in continuous time, but if you started to do this in discrete time, then you would say that the cost of transacting is proportional to the size of the trade. So psi t would be the size of the trade.
Mm-hmm.
So So think of it as, if you trade by in discrete states, it would be a jump, and then when you scale this, the term you get downstairs there, psi squared dt, instead you would get the quadratic variation.
Yep. Yeah, I did mean I know that there are approaches which do it like this. What I'm just repeating here is basically the simplest Algorithms framework that, like, I don't know when it was published, 2000 or so. Where it's, I mean, you can do, of course, a lot more sophisticated cost functions.
No, I mean, it's not more sophisticated or less sophisticated. It's that I think here, if you write down directly in continuous time, you think that's the only possibility. But in fact, if you start from a discrete model, there are different limits you can take. And one of them gives you this, the other one gives you some quadratic variation.
Yeah.
And they're essentially not the same.
They're not the same. I think there's another issue if you do the scaling, namely you have to have a market impact function that works both in discrete time, independently of the discretization of your time grid, and in continuous time.
Well, here, so if you think of market impact as the size of my trade divided by some impact factor, or multiplied by some theta. So if size of the trade over interval delta t and market depth over delta t, they both scale as delta t, here you're assuming both have a derivative, they are absolutely continuous, and then when we go to delta goes to 0, you get this.
Right.
Otherwise, you will get the...
Of course, I mean, this is, but I think this is why this approach was so successful, because they were the first, Chris, the first to come up with these a way of modeling this. I think, I mean it's rather courageous.
Will you go back to the other approach? Will you discuss the other asymptotics?
So the other one, this will be the fourth presentation, where we basically just assume that the accumulated order process is some measure, and so you may have discrete trades there. But then, depending on what this guy here is, yeah, the resulting strategies are not so different. You may have an initial trade at time 0, you may have an initial trade at the terminal time, but kind of in between, it sort of looks like this. Okay, but I mean, anyway, this is just to illustrate what stochastic control problems arise in these frameworks. And of course, it is not the most realistic thing in the world, and you make the model more realistic, you get even harder control problems that you can try to solve. But this is just the very simple, basic framework. Okay, so getting back to what they got, then they have this deterministic thing here. So now the goal would be to minimize this integral here, subject to the condition that the integral of psi has to be x. And that's a variational problem.
But psi t is random.
Sorry?
Psi t isn't random?
Wait, in this setting, it's going to be deterministic at the end of the day. Because there's nothing anymore here if you minimize this guy which has any stochasticity in it. Okay, now, but so this is just the trading cost. Normally, you would also add some risk cost to this. And here's just a list of possible, a very incomplete list, I should say, of possible cost functionals and benchmark price processes. So what I have shown so far is essentially this Ulrich-Horst model. They call their model mean variance, but I think it would be more appropriate to call it mean quadratic. Because they say, well, you have these liquidation costs, which is this term here from the previous slide, and then we add to that essentially a market risk term. And what is the market risk term? Well, S is a Brownian motion with volatility sigma, and so this is the volatility of your portfolio, this guy here, and you scale that up with a risk aversion factor. So you end up with an F function that looks like this. Input is a Brownian motion. For the benchmark price process, you want to minimize this. Okay, now many people have generalized this. So for instance, if you take another kind of risk measure, not mean variance, but some sort of time averaged value at risk, which was Jim Gather and Alex Sheet did, and plug in geometric Brownian motion for S, you get something that looks like this. So here we see now really that the S comes into the cost functional. Yeah. Here we only have the trading rate and the position. Here now, if we change the way we measure risk and the way we model our benchmark, we really have a stochastic term showing up in this equation here. Ankirchner Kruse basically did the same thing, but for a different driving process. So they have a cost functional like this, and then I think the most general setup is due to Alex Sheet. So the message basically here is depending on the input parameters of your model, you end up with very different control problems, but there is a kind of a common ground, and the common ground is you have very often just an additive form here where you have your trading rate plus some term which looks at the X, and this might be multiplied by some stochastic factors describing prices or liquidity or whatever. So the issue is not so much to come up with an even more general model and prove that an optimal liquidation strategy exists in this framework, but the idea is to better understand what the nature of the value function of these control problems is. So here's the model. And as I said previously, we would like to allow for both active orders and passive orders. Now, active orders are relatively simple because we, up to Rama maybe, agree on how to model the impact or the cost of trading actively in a market. You may talk about or discuss whether you want permanent or only temporary market impact or a combination of both, but in principle, we have an idea of how we do this. Modeling the impact of passive orders is a much more subtle issue. How does the market react to a limit order that you put into the book? I mean, it is known that order imbalances, especially at the first best price, at best prices, best ask and best bid price, these imbalances have some predictive power over future price dynamics. So it's not easy to model the impact of visible limit orders that you put in the book. This is why we choose this dark pool. So we say, okay, you can submit orders to this dark pool and they may or may not be executed. And if they are executed, they are fully executed, and they are fully executed with a certain intensity through some kind of Poisson process. Okay? So this is why we use this dark pool story, and why we are not arguing that you put a visible limit order into the book. People have done this, but then typically the idea is you put only a small limit order visibly into the book to avoid this issue of market impact of limit orders.
You mean that there's no impact of passive orders unless they execute?
There's no impact. There might be a cost associated with it, but there's no impact. But you have this uncertainty of execution. So if you trade maybe at a lower cost, but of course you don't know if and when you will be executed.
You don't know means you have some pride about it.
I'm sorry?
You don't know means that you don't know for certain, but
Yes.
But you do have some assessment.
Yeah, even that's tricky. So I try to get some information about the probability of execution in dark pools from practitioners. And they don't really give it to you. Because if you have, I mean, of course you have your own experience if you trade in these things, which should give you a way to estimate the probability of execution. But of course, there is no general statistics available about execution probabilities in dark pools consolidated through the whole US, because then it wouldn't be dark anymore, right?
Yeah.
But you may have your own experience for sure. But that's private information.
So excuse me, you assume that passive orders have no price impact? Is that
Yes, yes, yes.
Well, by construction, no? I mean, that's what the dark pool means.
Well,
No, but I mean, if in exchanges, I mean, for example, we did this study on exchanges with Stoikov and Kukanov, where you actually see that the impact of passive orders is the same as active orders. You cannot really distinguish them. So what contributes to the price movement is the order flow imbalance. So if I see a lot of buy orders being posted, even before they're executed, I will move my price. So
if
It's difficult to distinguish.
and we have another paper where we look at how to optimally hide limit orders in regular exchanges. Where you have a similar problem. If you show everything, you affect the order flow,
Yeah.
but if you hide everything, then you lose time priority. So in regular exchanges, hidden orders lose time priority over visible orders. So you have the same trade-off. And what we have shown in that paper is that depending on certain stock characteristics, you should hide anywhere between 20 to 80% of the order. But with the dark pool, it's different. So the dark pool is a separate trading venue. And of course, you can argue that even the liquidity that goes there has a price impact because that liquidity doesn't show up on the regular exchanges. So some dark pool operators, of course, argue that this liquidity is extra. It wouldn't be there if it were not for the dark pools. The cost associated with this dark pool trading, though, is pretty clear. Very often, and the practitioners call this adverse selection, the moment you get executed in the dark pool, you don't want to be executed. Because it basically tells you something about illiquidity in the dark pool. So if you get executed, chances are there is more liquidity on the other side of the market in the dark pool, which sooner or later will be cancelled there and traded through the regular exchanges, which then should drive the price into a favorable direction for you. Okay? Because there's more liquidity on the other side in the market, which shows up, hopefully, sooner or later in a regular one, which would be good for you.
I don't understand. I mean, there is no asymmetry of information. There are no informational considerations in this model. So why would you like to hide?
You order.
Yeah, but how you order? Why?
Because it has an impact on order flow.
But not
No, but the flow is not affected by whether you hide it or not, no?
Yes, because if you look at the visible book, yeah, and if you have a very balanced book, let's say you have only the best bid and best ask prices, you look at the volumes. If this is completely balanced, fine. If this is highly imbalanced, then typically you see a stronger order flow on the side of the market where you have less liquidity. So it's like an equilibrium condition, right? If it's really the liquidity supply is really out of equilibrium, the market tends to revert to equilibrium. So if you show a lot, typically the market reacts to this. So for instance, I put a really large order into the book. Now, you come into the market and you see me sitting there with this enormous order. You're never going to get behind me because the probability of you being executed, if you submit your order as a less competitive price than my big order, I have to be executed first, right? So you have to wait quite a while to be executed if you get executed at all. So therefore, you have an incentive to front run me, right? To put your order at a more competitive price than mine. And now you see how this price undercutting and front running and all these things, they're illegal, but they happen.
I see how it works, yes.
So this is why we want to hide, and since we do not want to have any interactions between active and passive order placement because that can lead to subtle arbitrages, we basically separate the market. The regular exchanges for the active order and the dark pool for the passive orders with no interaction between them.
Sorry, what is pi t there in the?
What is what?
In the portfolio dynamics, what is the pi t?
I'm getting to the. Okay, so we have our portfolio, we have our trading rate, just as on the previous slide, and this is basically the dark pool. So pi governs the execution, the order execution in the dark pool. So we just assume a Poisson dynamics. Every now and then this Poisson clock rings, and if at that time when it rings we have placed something in the dark pool, then it's going to be executed. So it's a very simple form of dark pool execution. It's all or nothing. So there's not a proper, this pi dynamics here doesn't depend on how much you put there. Okay? So there's just a certain probability of this being executed in a certain time interval. Okay? So these are active and these are passive orders. This is a rate, and this is block trading. There I really put like 100,000 shares into the dark pool, and depending on whether this Poisson process here jumps or not, I will get executed.
So sorry, in the dark pool, okay, you put your order.
Mm-hmm.
Do you wait forever? I mean,
No, of course not.
So when does this thing is cancelled?
So in the simplest case, the situation is you see this basically from the nature of the optimal control. But just to tell you up front, basically in the simplest case, you put everything you have into the dark pool, and then you just cancel slowly and trade that in the regular exchange. But you leave whatever you have in the dark pool. Of course, you're not going to wait forever. But what that dark pool does to you is that you trade slower, at least initially, in the primary venue, because you really hope for this dark pool execution. And all this depends strongly on the structure of the cost function, very strongly. I will comment on this as well. Okay, so we have a cost function. This is what we've seen previously. So this is the cost of trading in the primary venue. This is also what we have seen previously. This is the risk cost. Think of P as being 2. And this is our adverse selection cost trading in the dark pool. Now, the much I hated to say, but I'd love to have a 1 here. And in the last presentation I'm going to show you, we do have a 1 there. But the reason we put a P here, so we have the same powers, is for purely mathematical reasons. Because if we have the same powers everywhere, we can use the standard machinery to solve the problem. Some people argue that you should have the same powers. Some people say, no, you should not have the same powers. I think the most natural thing to have really would be 1 here, because what the practitioners do if they benchmark the cost in dark pools, again, they look at what is the mid-quote at the London Stock Exchange and how much did I get executed in the dark pool. And how much did I actually, not the mid-quote, what is the actual price I paid, but my benchmark is the mid-quote. So it is price minus mid-quote, which might be a stochastic component, like this one here, but then it's just the volume. Because we do assume that, or we argue that these dark pool trades should not have market impact. So I don't like the P here, but we just don't have any idea how to do it in reasonable generality if we have different powers there.
Could you just stop on this value function a little bit more? For example, what is the rationale of including this risk term? Is that because you associate risk with remaining position or something?
Yeah, I mean, if this is, if we go back here to the original model, so they, as I say, they call it mean variance, but it's not mean variance, it's really mean quadratic. So they say, well, the risk, you want to reward early liquidation.
You want to
reward early
yeah,
liquidation.
because you don't want the remaining position.
Exactly. So this is if you just think of mean variance, and this is just the market risk term here. Right? So we throw market risk in here in that form.
And the first 2 terms?
So this is, the first term is basically this one.
Yeah,
Whatever, yeah, this is the cost of trading actively. And the second one, this is the cost associated with dark pool trading. So if the dark pool trading really is free, then set this guy equal to 0, no problem, right? But there are these adverse selection costs associated with dark pool trading. I tried to explain earlier.
Yeah.
Often, yeah, so you take the execution of an order in a dark pool as an indicator for future price movements in the primary market. Meaning that the moment you get executed in the dark pool, you really don't want to be executed.
So,
But then why do you go into the dark pool in the
yeah,
That's
because
because
Well,
you're gonna know in the
because
future
of the
that
price
you never
impact.
get.
Well, it's a balance, right? I mean, it could still be cheaper. It might not be free, but it could still be cheaper.
but really,
So I give you a simple example. Suppose this is a 1, okay? Suppose, forget this guy here. Suppose you have a 2 here, a 1 here. So it is clear that if you have a really large order, you would much rather have it executed in the dark pool because costs are linear in order size. Okay? However, if you have a small order, you would much rather then execute it in the primary venue because costs are quadratic. And if you have the same powers here, it really depends on the interplay of these 2 factors. I mean, this might still be much, much smaller than this one, but there is still in practice this adverse selection cost associated with it. So I mean, the cost is there. The question is, what does it look like?
In actual implementations of this, how would you estimate these functions? because these are reduced form type model. These functions presumably reflect some underlying objective, intertemporal objective. No?
Which function? This
Yeah,
function?
the cost functions.
Yeah, I mean, here, this is really the main issue because
Um,
here,
So this is what?
this is really the main issue because, for example, here you, a more natural way of accounting for trading costs would be to actually look at the trading costs.
Yeah.
You sum the costs. So here, there are two types of costs. One is the actual cost, and then you square it,
mhm.
and then you add it to some risk number, which is a volatility expressed in price units. But then you're summing the squares. But if I look at the mark-to-market loss and the trading costs, they're both in dollars, and I sum them, it's not equivalent to this. So I mean, there are different formulations of the cost function, which can have completely different results.
Well, how can you justify this structure? Well, first of all, this eta, if we go back here, then we had this market impact factor, which can describe the height of the book. Yeah? So assume this height of the book varies randomly. Yeah? So this is relatively easy to justify.
Yeah.
Again, I'm not defending the P here because I know I don't want it, but so assume this is 1.
Okay.
What could this be? So imagine the following hypothetical situation, and we comment on, it's actually an example in the fourth paper I'm presenting. Suppose that, take this idea of unfavorable price dynamics upon dark pool execution to the extreme. So assume that each time you get executed in the dark pool, the benchmark price jumps. Okay? But your dark pool execution or order is executed at the old price, but the benchmark price now jumps. Yeah, so it really moves in an unfavorable direction. And if you do that, you end up exactly with a term like this.
Yeah,
Because
but then,
after,
no, sorry, but then if so, you say systematically this happens.
Mhm.
Then if this happens systematically, you should sort of introduce it into your considerations directly, not in this manner. No? So this is something about some systematic relationship between trade being conducted at the
Mhm.
postulated price and what happens with the benchmark price.
Mhm.
But here you're sort of, rather than modeling it explicitly, you are accounting for this indirectly.
Yes and no.
And
There is there.
no, just to wrap up my question. So I don't know anything about
Huh?
that, so I might be saying stupid things. But what I would imagine is that because of this, one very important concern would be to what extent the conclusions depend on the particular details of this formulation. Because if they depend, since it's a reduced form formulation, you are in a very fragile situation.
Okay, I answer your second question first. It depends on what you mean by conclusions. If the conclusions are here's a particular form of stochastic control problem, and here's how you can solve it.
No, the conclusion
The-
would
the
be
con-
what is
then
the
it doesn't
optimal-
depend on this
what
at
is the
all.
optimal- What is the optimal policy
The
or strategy?
you can also justify this by looking at a discrete time model, and this is actually where we took our motivation from, which was one of my PhD students did in his thesis. You look at a portfolio liquidation model in discrete time, and you correlate price movements or dynamics of the benchmark price with execution probabilities in the dark pool. Yeah? So this is not independent anymore, but conditioned on the execution, you have a higher probability of an up or down movement in the prices. And you do basically the algorithm Chris type cost functional, so this mean quadratic thing. You end up with exactly something which looks in continuous time like this.
Okay, so that is,
So this is the motivation number one, and I granted the motivation is much better in discrete time. And the second motivation that I could give was the other story that I just told. Assume that each time you get executed in the dark pool, the benchmark price jumps. It leads to the same. It leads to the same term here. And then you just add up the different costs to have something tractable.
So the gamma would be like the jump size, or
Gamma would be. I mean, the jump size doesn't really matter because if you assume for simplicity it's all or nothing, then it's essentially the intensity. Either the intensity or 1 over the intensity, I forgot. Because this is a Poisson process, it comes with a certain intensity.
still gamma is your cost, right? Gamma is the cost.
Yes, but if you never get executed, you don't have the cost. If you get executed very often, you have a higher
Right,
cost.
so then you multiply intensity times some kind of jump size, right?
No, the jump, this only tells you if you're executed. So this is a Poisson process. It just counts the number of execution.
Gamma there.
Yes,
The gamma is T.
yes. So this guy here just counts the number of execution. And it comes with a certain frequency or intensity. And the gamma would, in that model, basically be the intensity of this Poisson process here. It's not a jump size. The Poisson process jumps by 1.
Right.
The jump size is basically this guy here and this is here.
I think she was what I was imagining also it might be the impact of this Poisson on the price ST, something like that.
Yeah, you would sum
That jump size you mean? Yes, yeah, of course. Yeah, then it's a mixture of the intensity and the jump size on the price. Okay, sorry. Yeah, if this is what you mean by jump size, you're right. Sorry. Okay. So, good. So now, as I said, I mean, this is let's take the story as a motivation for the stochastic control problem that we want to look at. And let's just take this cost function that is given and take it from here. So one remark on the dynamics of the benchmark price. We make it a Brownian martingale. And of course, we have in mind geometric Brownian motion. At the end of the day, we would like to incorporate Black-Scholes. So we make an assumption here on the sigma term that it has this linear growth condition at 0. So we do not necessarily assume that the sigma is bounded away from 0. This degeneracy versus non-degeneracy assumption on the volatility plays an extremely important role if you look at models with BSPDEs. But I mean, if the discussion goes on like this, and I like it very much, then maybe I just skip the BSDE and move right away to the other model where we have permanent and temporary market impact and discrete trades and everything. Okay, so this is just a technical remark. So this is what I was talking about all the time so far. If our cost terms, the eta, the adverse selection cost, the risk cost, are deterministic, so in this setting we want to make them random, then you can actually allow different powers here. So you penalize trading in active orders square, risk cost, and here you have a 1. And if you have this structure and you have deterministic coefficients, you can still solve the stochastic optimal control problem. And this has been done in the thesis of Peter Kratz and also in this other paper, which I'm going to show you later. The point is, why does it work if you have deterministic coefficients? The insight from that is, with deterministic coefficients, there will only be at most one dark pool execution. So if you trade optimally, you put something into the dark pool, which depends on time, and if you get executed in a dark pool, you're never going to use this dark pool again. So there is a deterministic boundary which tells you that if you fall with your portfolio position below this deterministic boundary, dark pool trading is no longer optimal. And once you got executed in the dark pool and you trade optimally, you stay with your position below this deterministic boundary. If you make your coefficients random, and this is what you really use to solve this control problem in more or less closed form. If your coefficients are random, this boundary starts to vary. So there's absolutely no reason to assume that you have only one dark pool execution. anymore. And this is why the method that allows you to solve this problem with deterministic cost function just doesn't work if you have price-sensitive market impact functions. Okay? So this is why we put the same power there. Okay, so what is the value function? I mean, one thing is a bit subtle, one thing is very easy. First of all, if we have the same power everywhere, then it's kind of power utility type approach. So the value function will be some inflator times the state process to the power of p. This is what we would just guess from Markowitz, and this is clear. The question is, what is this inflator looking like? And for this inflator, you can set up a PDE. And setting up the PDE also is not difficult. The PDE we derive from dynamic programming. The PDE we derive from pointwise optimization. And the PDE is here. It's not so important what it looks like, but this is just dynamic programming. Assume we have this inflator, we have the optimal trading strategies in feedback form, and now we can interpret these results. Getting back to your question, like if we don't have adverse selection cost, so if this guy is 0, then of course these two cancel, and we always put everything that we have into the dark pool. It's clear. I mean, it doesn't cost us anything. We hope for the best, and if we get executed, fine. If we don't, then we cancel a little bit of what we put in the dark pool and trade it in the primary venue. And in the primary venue, we always trade a certain proportion of what we have, and the proportion depends on the state of the stochastic factor, which might be an indicator for liquidity, which might be a benchmark price process, whatever. Okay, so far so good. So what's missing here? What's missing is a boundary condition. So setting up this PDE, again, follows from dynamic programming. And what is supposed to give me a unique solution to this PDE is the boundary condition. But the boundary condition now is difficult because this value function here is supposed to go to infinity if x is not 0 at the terminal time. Fine. So how do we deal with this issue? And this is where Eric Siri came in. I mean, first of all, if we have our candidate optimal strategy, we just plug it in. So this term here just looks at the dark pool execution, and each time we get executed a certain fraction, namely this one here, of our position is executed in the dark pool. So forget this term for a second. This is what we have left of our position from trading in the primary venue. And we want this guy, suppose no dark pool execution happens, which has an event with positive probability. So the trading in the primary venue alone has to liquidate the position. So we have to have a condition on this trading rate here that guarantees that we end up with 0 at the terminal time. So we need this inflator over eta to go to infinity, in parentheses uniformly in price, to guarantee that we actually have that we actually can meet our liquidation constraint. And this is what rescues the control problem here, what rescues the PDE. So the PDE would be this guy with a boundary condition which has the singularity at the terminal time. But somewhat hardwired into the problem is a speed of convergence of the solution to this PDE to infinity. And the speed of convergence is this. So you know how this inflator has to behave, so if you reverse time, at the initial time. So it has to have a singularity, okay, but it has to have a singularity of a very particular kind. And this is good because if we would just state our boundary condition as something infinite, of course that's not a good boundary condition. What is this supposed to mean? We can do infinite, we can do infinity plus 2, infinity times 4. This should all give us the same thing. So how can we possibly expect to have a unique solution to a PDE with such a weird boundary condition? But there is a particular asymptotic behavior of that equation hardwired into the problem, which is responsible for uniqueness. So what is the intuition for this particular asymptotics? Well, first of all, if you have a deterministic problem and you solve the variational problem, it's just what you get. In a deterministic setting where you can only trade continuously, you always trade, and you have no risk cost, you always trade the same proportion of your your position, and you end up with the optimal solution of this problem, which has exactly or precisely this asymptotics that you want. Now, if we have stochastic cost terms here, to get an upper bound for our value function, we just assume that we are not using the dark pool, so cost can only increase. We plug this particular trading strategy into our cost functional. So then this is the trading strategy. It gets multiplied by the trading cost. This is how much is left at the time little t. This is how much gets amplified by the risk cost. So we have an upper bound of this form for our value function. This term we can certainly forget, that goes to 0. So we only have to look at this term here. Well, for this eta here, so this is deterministic, so we move the expected value in. We plug in the supremum of the expected value, have a t to the power of p here, integrate this constant here from 0 to t, so this is what explains this one here. And then we just expand this guy here, basically using e to the martingale property of the benchmark price plus some assumptions that we made on eta. Okay? So this is why we're going to end up with this 1 over t to the power of p minus 1. For the upper bound, for the lower bound, it's very similar. For the lower bound, let's say we throw away adverse selection and risk cost. So this is our cost functional here. So we put in the smallest cost that we can have, apply the continuous version of Jensen's inequality, and look at the scenario where we have no dark pool execution, which happens with this probability. So we have a lower bound like this, and again we expand this guy here with Ito and use Burkholder, Davis, Gandhi to essentially replace this guy here by a constant. So we do know that if we have a solution, or that that our value function, if it exists, it has this weird boundary condition, but it must have a particular asymptotics at the initial time or terminal time, depending on which way you do it. And this allows us to solve the whole thing. So the main theorem is, after the change of variables, reversing time, we can set up the PDE for this inflated term with this boundary condition here that is supposed to converge to infinity uniformly in the space variable, so uniformly in the price. We have a unique solution for this, and this unique solution automatically satisfies this asymptoticity condition here at t equal to 0. So initially we thought that we have to impose this as an extra condition, but as it actually turned out, this is not necessary, because this asymptotic behavior is already somewhat hardwired into the problem. So this is what this remark just says. Initially, as I said, one should think that this is just a very, very bad boundary condition. Infinity, 2 times infinity, whatever. It's too imprecise. But because of the nature of the problem, we do know much more about how this function behaves at the initial or terminal time. And this is what really gives us uniqueness here. So how do we prove it? There are basically 2 possibilities of doing this. The first possibility is you look at a model where you replace this singular terminal condition by a penalization term. So you penalize whatever you have left at the terminal time by some large factor n, and then let n tend to infinity. Possibility number 1. Possibility number 2, what we suggest here in this paper, we make some sort of an asymptotic expansion of this PDE at the initial time. And that avoids certain problems that come with the use of the stochastic penalization method. So the idea is, okay, we know how this function behaves near t equal to 0. So here, this is this asymptotic that we have motivated previously. And then we correct. So there should be a correction term that makes this a valid equation. And now we try to get our hands on the correction term. Good. So we write our inflator as the asymptotic term plus some correction, and we want to understand what this correction term u here is. And there's a dirty trick. The dirty trick is, in principle, u is completely free, so we could write down here t to the power of 1 over beta. The dirty trick is to write 1 over beta plus 1. And I'll show you in a second why this dirty trick works. Because if we write this like this, we have some idea of how this function u behaves at t equal to 0. It has to grow at most quadratically. So we have a PDE for this. So we can write a PDE for this. And if you do write a PDE for this, we get a nonlinearity. Call it f. It's not important what f is. This one. What is important is that we have a power series here in this nonlinearity, which has a singularity. So it is u, the function that the functional term in the PDE nonlinearity, over t. So we have a singularity here in the nonlinearity. So the point is that we move the singularity from the terminal value. Here we had no singularity in the nonlinearity for the PDE, but we had a singularity in the terminal value. So we move that singularity from the terminal value into the nonlinearity for the PDE. But we move it into the nonlinearity in such a way that it causes no harm, because we are looking for a solution u which satisfies this quadratic growth condition here. So we know that close to 0, u is something of the order t squared, and we divide it by t. So we don't bother too much about the singularity here. So we are shuffling around singularities, but we are shuffling around singularities in such a way that it causes no harm to us. Okay, now once we've set up this equation, okay, we have a more or less standard PDE, except that we are looking for a solution in a non-standard space, and we are looking for a solution to this PDE in a space of functions which have a particular growth condition. Okay, and then it's a standard fixed point argument to show that this solution really, this equation really has a solution. There's one subtlety though, namely the value function is the product of two terms, the inflator and the position. The position goes to 0, the inflator goes to infinity. Which one wins? Yeah? You have to make sure that the value function really is 0 at the terminal time for x equal to 0. But you have these two competing terms. Again, inflator goes to 0 and to infinity. The position goes to 0. So the position in a way has to go to 0 faster than the inflator goes to infinity to guarantee that the value function does what it's supposed to do. And that needs another argument, and the argument is that, first of all, you can consider only strategies that give you monotone portfolio processes. So this is pretty obvious. I mean, you want to unwind a position, why should you buy? I mean, you have to formally prove it, of course, but this is very intuitive. And for such strategies, you have this condition here, what I just said. So this guy goes to infinity, this guy goes to 0, but still, altogether, it goes to 0.
This is intuitive, but as you know, there are models where you can have, you can buy and sell and generate profit on average. So your structure excludes that. That's what you're saying.
Well, I mean, we prove it, number one. Number two, I know a model where this happens, which, for instance, in this Gather a Sheet paper, but this is because they put the wrong risk term in there, they should have an absolute, when they say this, they should have an absolute value where they did not put an absolute value to preserve differentiability. And because of that, they actually unwind the position, then they become negative, and then they revert back to zero. So this is because of the specific kind of ill-phrased optimization problem.
You have nonlinear price impact, you can have that, right? Because you can send small orders to buy, and then you sell a big
So
block.
I would say
Nonlinear,
if you have a model where this happens, it's not a good model. Because if you think of agency trading, it's simply forbidden. If I come to you and say, sell my portfolio, you are not allowed to buy. So in agency trading, that's illegal. So if the model does not give you this property automatically, I think you should enforce it.
enforce it in what way? Enforcing doesn't mean you
Well,
deny that it exists. That's the difference.
No, whether it exists or not depends on what admissible trading strategies are. And if you just do risk trading, so you trade on your own account, then that's fine. If you do agency trading, it's not allowed. So in models of agency trading, you should have an extra condition on the set of admissible trading strategy that tells you can only be on one side of the market. But I mean, sure, if it's just risk trading, yeah.
I
And-
just noticed because like the papers you said, Anker and Chris, they proposed this nonlinear impact model.
Mhm.
But you can see easily that if you have nonlinear price impact, then if you sell in small quantities and buy back in a big quantity, then of course you can.
Also, if you have both active and passive orders in the same market, same thing can happen. But again, I think the question is, what situation is the model supposed to model? And if I have agency trading in mind, then it's a requirement that you're always only on one side of the market. Everything else sends you to jail, at least in the US. Okay, but in this model, it holds automatically. In the model I'm presenting last, it may not. So you may actually buy and trade in the same model, depending on the market environment. But we are going to get that later. Okay, so I guess this brings me to my first conclusion. So what have we seen? Well, as I said at the very beginning, we look at a stochastic control problem motivated by portfolio liquidation. So the motivation for the precise nature of the cost function might not be the best if you really think of portfolio liquidation, but the characteristic feature of these models is the singularity at the terminal time. And what does it mean to your control problem? And what this paper suggests is this asymptotic expansion of the value function, which avoids certain problems that come with the penalization term if you penalize terminal holdings by a large factor. What we are currently working on is introducing permanent market impact. So this was a model where you have only this temporary market impact. I trade, it cost me something, but then the impact is gone. Which, as I said repeatedly, is a major open problem, is really to have different powers for active and passive orders. Because then the separation argument, state sequence multiplied by inflator, just doesn't work anymore. I think you can still do a stochastic maximum principle in the characterization of optimal trading strategies, but whether you can show that all these adjoint equations that show up in these models have solutions is a different question. To understand a little bit better what the structure of the trading strategy is, I asked one of my graduate students to simulate the model. So to see whether this deterministic boundary that we get in a model where we have deterministic cost functions. If it starts fluctuating, how much of an impact this really has on your trading strategies. But he's a little slower with that than I was expecting, so I cannot show you any pictures about this. Okay, so this brings me to the end of my first presentation, and we are almost through for the morning session. So are there any further questions at this point? Okay, if this is not the case, then I would suggest maybe we conclude here and reconvene at 2. And I changed the order of the talk, so maybe I'll present the other model first with the permanent and the temporary market impact, also where we have more general trading strategies, including jumps at the initial or terminal time. Okay, well then, thank you very much, and see you at 2.